talking to probably loads of you saying, hey, I can help you with your go-to-market and all the stuff that you hear constantly. And I thought, well, I'm one of so many people doing this, and I get all the emails from consultants saying, I can help you with your go-to-market. I think, okay, great. So I thought, what's a better way to do it? How to stand out from the crowd and put my money where my mouth is. So I started a consortium where I curate, I find what is the next generation technologies. Now, whether that's in direct physics, whether that's in data science, or whether that's doing something completely different that nobody else is doing. I've got three main criteria for the consortium. One, if it's direct physics, it's got to be 100 times faster than the incumbents out there. That's not actually that difficult anymore. The other one, if it's not 100 times faster, it's not direct physics, it has to do something that nobody else can do. So it's an optimization that nobody else can do, something such as that. And most importantly, it has to be complementary to the rest of the stack. So if I'm going to companies and I'm going to an engineering company, I'm going to a Ford, I'm going to a Boeing, whoever it is, and I'm saying, I have a technology stack, everything in it is going to be light years ahead of what you're doing there. And that's essentially the synopsis of the, I say synopsis, that's a terrible word to use. That is the overview of the consortium where it is at the moment. Little bit of history on this, and I love this. I've got to say, AI helped me find this information. So I'm taking two different types of solvers here. One CFD, fluid dynamics, one electromagnetics. Now, incumbents in this field, Fluent and CFX, Star CCM, they're the incumbents for CFD. 25 years old, at least. In electromagnetics, HFSS, FICO, CST, again, 25 years old. These are old solvers designed for old computing power. How have we not moved forward so much in a quarter of a century? The answer is actually really simple. Companies have not had the tools and the cloud tools and the amount of development tools in the background to be able to develop new software and rival software quickly. And there is now, so we're getting a glut of new things now. On the AI side, this was something McKinsey came out with last year. So this was about almost exactly a year ago. McKinsey did a survey of various engineering companies who wanted to explore AI. So this is not large language model AI. This is not your ChatGPTs, your Claudes. This is deep learning physics. This is the stuff that NVIDIA always posts lots of pretty pictures about. 95% of those fail or have failed and are still failing. I know this. I know this for a fact. I've experienced this for when I've been working for a company that I mentioned earlier that I'm not going to mention now because it seems a little bit wrong. But most of these fail. And adjusting why do they fail and understanding why they fail is a real trick. I will come back to that. Those of you who are friends with me on LinkedIn, or connections on LinkedIn, I'm not allowed to say friends, they're connections, sorry, may have seen this software map. I'm one of the architects of this software map, and it's been copied all over LinkedIn quite a lot, which I think imitation is the highest form of flattery, and I'm going to stick by that. This was from last, I was about to say autumn, but last fall. So this is 6 months out of date. There will be a new one coming up, but you can see the amount of technology companies in this space. See, Aris is here, so Aris is present, and some of you in the startup world may see your logos on here. I've got some edits to do because there's been further acquisitions in the space. There's been some companies who also maybe have gone a little bit downhill, so there's updates to do with this, but you can see the technology landscape is pretty huge. Now, not 100% of these companies have something valuable to offer. Some have got a great idea, but not all of it works. So I tend to filter through this. I speak to as many people as possible, and a lot of the time, some really good tech out there. But does it fit the market? Does it fit a need in the market? This is always a question I ask. This is something I came up with when I was trying to explain how to do successful AI for engineering. Now, one of the biggest failures for AI and engineering, why a lot of these companies are not getting the ARR, I'm talking deep learning, I'm not talking the large language models, is they focus on this bit, the data sciencey bit. I'm sure there's better technical terms than that. But that data sciencey bit is all well and good, but there was a occasion where there was a POC for a company, who remain nameless, who had hundreds of samples, and this is automotive aerodynamics. They had hundreds of samples from a company, and they weren't getting the predictions. Simply weren't getting the predictions, even on the test set. I say, okay, how with 500 samples of one model are you not getting the predictions right when you put some test ones in? I remember looking at the results, and I was the only engineer at that time having a look at it. It's funny, the sales guy is the only engineer. But I was looking at it and thinking, okay, you're just training on surface data. I knew that in aerodynamics and automotive aerodynamics, you've got to look at free field data because there is what we call the pressure drag. So like when you're standing on a train station, train comes past you really quickly and you kind of get sucked toward the train. That's the pressure outside the train kind of sucking you in, as it were. That wasn't taken account from, and you can't predict that without knowing the free field aerodynamics on that. I had to say that, and that, once we added that bit, the engineering bit, it worked. And we said, okay, we're just going to change the type of data. We're just going to change the way we look at the data. We're going to change our understanding of it. So this is when I thought, actually, there's no substitute in any of this for domain knowledge. And knowing what you're talking about, knowing the products you're talking about, and understanding your customer. I think Peter said this earlier, you've got to be able to empathize with your customer and empathize who you're dealing with. If you can't do that, you're not going to understand the problem, they're not going to trust you, and nothing's going to work. So the AI world, it's slowly getting toward that, and I've noticed in the AI companies that are doing this, they're doing a little bit more domain specific. And then you've got the overlap, which is the data processing and the data analysis side. And actually having the right data processing tools when it's a completely disconnected digital thread, as was said earlier. Most companies use lots of different simulation technology. They use test technology and so on. How do you put all that data together? And how do you make it coherent? And I'm going to go through that a little bit. Risk. I love talking about risk. It's something very easy to talk about, very difficult to deal with. This is a risk model, again, I put together to highlight on the CAE market. So this is the engineering part. This is this physics simulation part. This was the original way we did it back in the 80s, 90s. This would be your product development curve. You spend money, you build your first prototype. Okay, you fix some stuff. You build your second prototype. You build your validation prototype. This is when everything goes brilliantly. Your validation prototype, everything works wonderfully. Start a production, boom, your costs go down. What happened 9 times out of 10?
One of them came up.
Big overspend, big risk. And that's why the whole industry started left shifting. So left shifting was essentially, we spend the same amount of money, move this curve to the left, and we reduce the risk. Because we're simulating everything up front. Advanced CAE got really, really good. And the physics simulators got fantastic. You could predict pretty much anything as long as you had the hardware and the patience and the expertise to do it. That was great. That's still where we are at the moment. Now, the promise of AI is further left shifting, but also squashing this whole curve. How can we both reduce the timeline of the models and reduce the overall cost? This is the AI promise. And it's like, great, this is the AI promise, we can do this. AI is going to solve everything for us. But what comes with AI? And this is the real trick. What comes with it is an even bigger risk bubble. Now, the amount of companies who spend 6-7 figures on AI initiatives, but their data isn't right, or their data isn't organized properly, or they don't understand their data, that's the trick there. And that's the reason why there's such a big risk. Because AI companies, and I go including NVIDIA, They promise all this stuff, they promise these amazing models, look at all the stuff you can do, but without the fundamental data behind that, it doesn't work. And what I say on deep learning models, on physics AI models, they're dumb. I actually call them dumb AI in most of my work because they know nothing without educating them. Now, those engineers in the room that spend 5, 6, 7 plus years at college learning, you spent all that time learning, and think about the amount of data you've ingested over that time, and it's significant. You've seen lots of different examples and so on. AI needs that data, actually needs a lot more data, because although it's supposedly can think for itself, it can't really think for itself. You've got to tell it, and you've got to organize that data, and this is why what was said in the ARAS presentations a little bit earlier was really interesting. We hold all the data, now what do you do with it? How do you actually make something work? And that's the really interesting thing. I'm going to talk more about risk. I'm sorry. Does anybody recognize this model? Swiss cheese model. I think it's a great model. It's actually mainly got used in COVID. And it was a model that they used to manage risk of infections in hospitals and public places and so on. It's a really interesting model, and I decided to adapt it for AI for engineering. So 5 really simple steps, and I give these talks to engineering companies to actually help them identify where they need to use AI and so on. So the first thing I say, the application you want to use AI for, is actually valuable? Are there direct physics and direct physics simulations that are quicker than using AI? And this is a fundamental one, and that question isn't as easy as you think it is. Because as I said earlier, there are new solvers coming out that are 100 times faster than the incumbents. So actually the answer to this question may not be what they've got at the moment, but it may be that there is a tool that can be a lot quicker. Then data volume. How much data do you actually have? Now, is there a critical mass of samples for certain applications? Yeah, there probably is, after which you get diminishing returns. Can you combine synthetic data, so simulation data and test data? Various other conditions of that data that says, do you have the volume? Now, what's really interesting, that you may have 10,000 bits of data, but you've got some different conditions on them. You may actually only have 100 bits of data. And this is where some good domain knowledge needs to come in. Data quality. Is the data any good? Has it got lots of errors in it? Because when you get 10,000 bits of data, if it's all got 10% error in it, you're multiplying that 10% error by 10,000. And it becomes a little bit useless. So quality is incredibly important. And uniformity. Uniformity comes back to volume. If your data isn't uniform, then you actually don't have a critical mass of data. So how do you sort the data so it's uniform, it can all be read together? And this also goes back to the large data sets when you've got lots of different sources from it. And that's very important. So can you bring the data together in a coherent form that can all be read together? And last of all, would machine learning or reduced order modeling. By the way, machine learning and reduced order modeling have been around for at least 20 years, but they're now all called AI. Which I think is all a little bit funny, but machine learning, reduced order modeling, it's a hell of a lot quicker than AI. Doesn't require deep learning, doesn't require neural networks, and can be done without really, really expensive tools. Once you've gone through all this, then shoot for the deep learning, but not until that. So it's a risk model. I present this to kind of the C-suite in certain of the larger engineering companies to help it make sense, because a lot of the C-suite in these companies, they're not engineers, they don't understand all of this. So I help try and translate it for them. That's actually the end of my overview, because I only have 15 minutes to go through this. Now, I do run a consortium. There's 5 companies in the consortium. I'm happy to discuss all of them, but they range from next generation physics companies. I'm very happy to have the CEO of one of the consortium companies in the room. Masha, make yourself known. But I also deal with a company that is a data science company for engineers. So it will read all the different file types and so on, makes them into a coherent, uniform data set that can then be used for deep learning and physics and so on. And it takes, each one of these companies that I work with, it takes me a good little while to get my head around the software, and I fundamentally believe, and I think this is the same for all startups, if you can sell your software, sell your tools to yourself, you can sell it to somebody else. If you can't sell it to yourself, you can't sell it to somebody else. That's all from me. Thank you.
We could probably take one or two questions, if anybody's got a question for Andy. Go ahead. Oh, here.
It's a quick one, but that 95% failure metric you found in terms of data failures of the AI companies in that space, can you talk a little bit more about, I know from experience you found that with the specific 95%.
That comes from McKinsey.
McKinsey, okay. I didn't catch that, thank you.
Anybody else?
Based on the amount of data sort of that you need to do this well, does that kind of eliminate smaller engineering organizations? Like, is this only available to organizations with a lot of data, or is that the wrong question to ask?
What do you mean? Are you talking about smaller engineering companies?
Yeah, or like, is there a critical size where it actually is, feasible for surrogate modeling?
Completely depends on the application. Depends whether you want to do a surrogate model for structural dynamics, fluid dynamics, electromagnetics. Depends on the application. And actually, what I normally advise companies is start your preparation for AI for deep learning now. Build the data, store the right data, organize it in the right way, and then in 1 year, 2 years' time, rather than having to make this huge investment in AI and so on, the data's all there sitting there. And particularly with models like Physics Nemo from NVIDIA, which are basically, they're not free because you pay for the hardware, but they're free from a software point of view. You can try it whenever you want. So it's having the right data strategy is the key part to any deep learning. And it doesn't matter the size of the company. I know a company which is a startup making actually Carnot engine cycles, which is an uber efficient engine cycle. That company is maybe a year old. They're already starting to use machine learning models and building up to AI models. So I don't think there is a minimum size. I think it's just how you put things together. And the really interesting thing is, so I know a few OEMs and I work with few OEMs. In theory, they've got a lot of data, but it's all in PowerPoint. And they've deleted all the actual files. So actually all their data is absolutely bloody useless. And they're having to start again. So it doesn't matter company size. It matters how they save the data and what they do with it.
Data governance, right? That's the name of the game.
Yeah.
Everybody here knows the difference between physics-based modeling and surrogate modeling. It's not a mystery to anybody. So I don't know.
I had a question about that actually.
Yeah, okay. I thought there would be.
Thanks. So actually I was going to ask you, you talk primarily about basically database modeling and such. How do you see the field of physics-informed machine learning kind of transforming this period?
Oh, physics-informed neural networks.
Ooh,
I haven't
pens.
seen one that works yet. I'm going to put it that way. I remember seeing a paper, I think it was only last year, where a physics-informed neural network still couldn't do the flow around a bent pipe. So I'm not dismissing them completely, but I have not seen evidence of them working yet. And I've got to say, if it's a physics-informed neural network, it's still solving the partial differential equations. So isn't this going to take even more effort to get working? It's a debate to have, but I don't see them coming into their own yet.
Oh, and sorry, just one last thing was a little bit different question, but also you kind of talked about it, but on the compute side, the compute resources side, as we know from like LLM, Gen AI perspective, there's a huge need or demand from the compute. What are your thoughts on, from the engineering perspective, the need for a huge amount of data centers and such?
I think that's a great question, and it depends what solvers and what tools you're using. If you're using traditional incumbent solvers, then yeah, you're going to need massive amounts of CPU, you're going to need these HPC farms and so on. If you're using the next generation of solvers, the next generation of solvers are working on GPU workstations and are really taking advantage of what GPUs can do. So I think with the direct physics solvers, the next generation, isn't as reliant on these huge server farms and so on. And particularly where a lot of the businesses now in physics simulations, a lot of it is in obviously in defense, which means closed areas, which means those big server farms just aren't even available. And you've got to be able to fit in the large simulations and so on the hardware that's actually physically in these closed areas. So, and I would argue that the next generation of physics simulators, and it's not just what I think is happening, it's what I'm actually seeing at the moment. So I'm seeing that in electromagnetics, I'm seeing that in fluids, I'm seeing that in explicit dynamics, which is the kind of impact-based structural. They all have new solvers coming out, which are GPU-based, which will work on a single head node and don't need these huge server farms. So actually, I think the hardware requirements are maybe coming down, but only for companies who are embracing kind of the next generation technology.
Thank you very much. One more round of applause.